Hey guys, welcome to Safi Mixed. In this video, I want to find the relation for finding the trajectory of particles under the condition of constant force. So I would like to find different relations for two different dynamical variables and would then specify the trajectory of the particle under the condition that the net force acting on the particle, that I would write it like F is always constant. That is, I want to use Newton's second law under this condition and construct relations for different dynamical variable and discuss the trajectory of the particle. With this condition, from one of the differential forms of Newton's second law, I can write dv over dt equals f divided by m. And I want to use this vector equation for one dimension and reduce it to just a scalar equation. And preferably, I would like to write this for x-axis. So I can rewrite this equation for one dimension in the form dvx over dt equals f sub x divided by m. So I dropped the vector notation. Now I'm dealing only with a scalar equation in one dimension. And for further mathematical simplification, I drop the subscript x from this equation. However, this should be in your mind that we are dealing only with one-dimensional motion and preferably along the x-axis. So that gave us the benefit to drop the vector notations. Now, since on the right side we put f is equal to constant and m for a particle is constant, therefore this ratio is constant, and we write this ratio as acceleration a, and this acceleration should be along x-axis because we are dealing with f along x-axis. Then I can write this equation in separable form by separating the derivatives. I can write it dv equals a times dt. Okay, now we know from calculus that if we know about the initial conditions, we can straight away integrate this equation. And let the initial condition for velocity be vi at time ti and vf at time tf. Then with this information about the variable vi, I can integrate this equation in the form from vi to vf, but keep this in mind that this vi and this vf are also along the initial velocity along x-axis and the final velocity along x-axis. So I write this dv equals a integral from ti to tf dt. I have taken a out of the integral sign or to the left of the integral sign because a is constant. It is independent of time. That's why I can write it like this. And now this is very straightforward. This gives me v from vi to vf, and at this side I write t from ti to tf. And if I substitute the limits, I can write this as vf minus vi equals a times tf minus ti. Or I can rewrite this in the form, let me write this on this half of the board, vf, and I'm taking vi to this side, equals vi plus a, and this duration from tf to ti I'm writing as t. So this equation describes the behavior of velocity with the passage of time, and you see this is a straight line equation with slope equal to a. That is, if I plot this equation on the velocity time plane, I take t over here and v along the vertical, then this is a straight line with vertical intercept at this point. This is vi, and the slope rise to run is in fact a. del V, A equals del V over del T. So A is the slope of the line on velocity time graph or velocity time plane. And this equation, remember, now there is one thing that you must note. If the time, if acceleration is constant and the time keep on increasing and increasing and increasing, the velocity will obviously keep on increasing. So we can, as per this equation, we can get infinite velocity, or we can give infinite velocity when t tends to infinity. And that's of course not possible because special theory of relativity restricts that nobody can take with speed or velocity greater than the speed of light. That's why we say that this equation is valid only in the non-relativistic region. So we use this equation in the non-relativistic regions, and relativity things become different then. Now, this is the equation for velocity or for the dynamical variable velocity. Under the condition that force is constant, remember this is the condition. This is very important condition. We can use this equation only if the acceleration of the body is constant. Now, I can rewrite the final velocity as a function of, since the final velocity is a function of time, therefore I can express this velocity in terms of the derivative of position. I write dx over dt equals vi plus at. And again, if I multiply both sides with dt, I can write this in the form dx equals vi dt plus a times t dt. Again, if I know for the initial information of a position and at the initial time, then I can integrate this equation. That is, if we know the initial condition of position at initial time ti, we can find the trajectory of the particle or the position at any time t, and let xi be the position of the particle at time ti and xf be the position of the particle at time tf. Then I can integrate this equation formally by writing xi to xf dx equals, again, vi is the initial velocity and that remains constant. We call this the integration constant or the constant of integration. So it is constant, and I can take that out of the time integral ti to tf dt plus a times integral t dt integrated from ti to tf. And this is now very easy. The result of this is x integrated from xi to xf, and the result of this is, let me write vi is t, and I write this as ti to tf, and plus a times, this gives me t squared divided by 2 integrated from ti to tf. Okay, now if I put the limits, I can write this as xf minus xi equals vi times tf minus ti, and I write this as plus half times a, and if I substitute the limit in this, I write it as tf squared minus ti squared. Or we write this in finally in the form xf equals xi, I'm taking this to this side, plus vi, and I reduce this to only t, that's the duration of time, plus half a, and I write that as t squared. So this equation gives us the trajectory of the particle, and you see the trajectory is in fact quadratic in time. So this is a sort of parabola. Since we don't have time in the negative part of the Cartesian coordinates, therefore this is always positive, and you can say this is the positive half of a parabola. One thing you must have noted, that solving this equation I use once the initial condition, and then solving this equation I again use initial condition. So in order, and this is in fact a second order differential equation in position. Therefore, to solve a second order differential equation, we always need two different initial conditions, one for the first derivative, in this case the initial condition on velocity, and one for the position derivative, that is xi. Okay, now if I plot this equation, obviously this is a parabola, and you see with the passage of time, this term contributes the most. It is t squared, so it becomes parabolic with time. Now I can eliminate, let me call this equation 1 and this equation 2. I can construct another very good equation, very useful equation, by eliminating time from this equation. And that I can do, let me write this over here. From equation 1, I can write t equals Vf minus Vi divided by A. And if I use this value of time in this equation, I can simplify this equation x if, and I'm taking this to the right, to the left, so I write this as xi equals Vi multiplied with Vf minus Vi divided by A for this t, and then I write, let me write this term here in the next line, half time A into Vf minus Vi divided by A squared. So I write this as 1 over A into Vi Vf minus Vi squared and then plus, here I would have A squared, and that A squared, and the square of that A squared would cancel with this A, so I'm left with 1 over 2A, and this would become Vf squared plus Vi squared minus 2 Vi Vf. Now, again, I can take A common from all of them and write it as A. So I'm left with Vi into Vf minus Vi squared plus half Vf squared plus half Vi squared, and this half multiplied with this 2 would make it 1, so I write minus Vi Vf. I can cancel this term with this term, and combining this term would give me minus half Vi squared. So I write, and I'm taking half common, I write this as 1 divided by 2A into, from this term I get Vf squared, and from this and this term I get minus Vi squared. So finally I call this thing as x distance, so, and I'm taking this to this side, so I write 2A times x equals Vf squared minus Vi squared. This is another relation that links the two different dynamical variables for constant acceleration x and v. So it links the dynamical variable v and dynamical variable x through acceleration a, constant acceleration. Now, this equation is independent of time. Therefore, it gives the average distance in terms of initial and final velocity. X is the distance. So it is lacking the instantaneous information of distance or the instantaneous information of velocity. Whereas this equation provides the information for instantaneous distance. Similarly, this equation provides information for instantaneous velocity because time is present at this position, time is present at this position. So equation 1 and equation 2 provides instantaneous information about the corresponding dynamical quantities, whereas equation 3 provides average information about the dynamical quantities. So for constant acceleration, but remember, we use these relation only when the acceleration is constant. If the acceleration is not constant, we cannot use these equations because we solve Newton's second law based on this condition. Now you can replicate the same calculation for y component and for z component. You will get a velocity, a same relation for the y component for velocity, a same relation for the y component of position, and then you can vectorially add the three components to construct general relation, vector relation, and I just want to write that equation over here. For velocity, you would have this relation Vf equals Vi plus At. And similarly for distance, you will have R equals Ri plus Vit plus half At squared. So you would have these vector relations for three-dimensional motion of a particle. And then, if you haven't yet subscribed to SophieMix, kindly support the channel by pressing the subscribe button and hit the like button on the video too. Thanks for watching.